I'm Marcus Runefors. I'm with the Division of Fire Safety Engineering at Lund University, and I'm focusing totally on hydrogen safety. So this will be really short, but I hope it will be informational. I'm covering a lot of different areas. I have one slide on on different topics here. So how many of you have heard of hydrogen embrittlement? Yeah, I got some nodding here. Because I think this is a very important. It's not my specialty, and it's very, very complicated. So I'm glad to hear that you're working together with Forte, who is good at this. So as soon as you have hydrogen, you all know that it's very small and such. When you have high pressures and strains and everything, it will enter materials. Most non-metallic material, it will simply just diffuse through. So if you have a tank of hydrogen, it will diffuse through, always. Not enough, not a lot, but it will diffuse through. It will also go into steel, and that different things can happen here. One thing is that it happens the same thing as it did for non-metallic materials, that it diffuses through. This is a pipeline steel where they put a tape on top of it, and I think after 24 hours you have this bubbling, and that's hydrogen bubbles. So this is something we expect. The thing we don't want is the hydrogen, and this will be atomic hydrogen when it enters the material, got stuck into the metal lattice, because that will affect, this is essentially an alloy of a metal. So if you want the steel to be able to move a little bit, because you have vibrations and such in these kind of systems, so you want a lot of ductility in your piping. But what happens when hydrogen is stuck into the metal lattice is that it becomes fragile. So it will burst very easily. So we'll have a different type. It can also collect in different type of defects in the metal, and you can have this phenomena that is called a blistering phenomena, where the atomic hydrogen recombines to hydrogen gas, and you can have blisters that burst. So it's extreme. I cannot go into too much details here, but the important thing is here in this note, that always use rated materials when you have a hydrogen installation. I know for a fact that there are several new hydrogen installations in Sweden who have not rated materials. So this is a major problem, because you don't want this to happen. We already got presented the flammability limits of hydrogen. And what is most important is, of course, the lower level from a safety perspective. So one thing one can ask is, what happens if we're above this 4% lower flammability limit? Will we have these kind of huge explosions? No. Between 4 and 6, we will have very small, nice flame balls traveling up into the stream. If it's totally resistant, so it's no air movement at all. If we have air movement, we will not have any ignition at all. If we move a little bit further up, maybe to 6 to 8%, we will have a very nice flame vortex traveling out as a ring. Still nothing of safety relevance. So we need to be above 8%. So this is where we should put out when we look at safety distances and things like that. It's a very broad international consensus that we should use these percentages. And this is often called the lower hazardous limit. So this is quite important. And the reason is that the flammability limits are directional dependent, since the main mode of heat transfer here is convective. So we have 4% is only upwards. Above 6%, we can also transport a flame horizontally, and we have to be above 8% to be able to make it travel downwards. And this have a low hazardous limit. This, of course, have a huge influence on the safety distances. So this is, I don't remember the pressures here, probably 1 millimeter and 700 bar. So here we can see the 4% limit, which is the lower flammability limit, which will give us roughly 6 meters of safety distance, and the 8%, which will give us 3%. I know there are, because our field likes to be conservative, and that's good, but there are a lot of people who want to use half the flammability limit. So they want to go to 2%, and then we're out here at 12 meters. So we can cut our safety distances by a factor of 4 through this, which is good. As you all know, hydrogen has a very low density. So sort of the gut feeling is that as soon as we have a release indoor, we will have a very homogeneous cloud up here. But that is actually not accurate at all. We will have quite not homogeneous. It will have a gradient, but it will not at all be like this for real releases. If we have a very slow release that are dominated by buoyant forces, we might have a quite distinct layer, but that would require our release to be in the order of a few bars or less. And we don't store hydrogen at a few bars because, as you all know, the volumetric energy density is negligible. So we need to store it at 300 to 1,000 bar. And as you saw at the previous picture here, going back, we don't see any buoyancy behavior here. When we have a release, it will go on. It's dominated by momentum forces or inertial forces until very, very low concentrations. And when you have very low concentrations, you have very little buoyancy. It's actually not that buoyant when it mixes so much with air. And it's also very diffusive, which is also very important. So that's why we will see a more or less homogeneous, not homogeneous, but somewhere in between. We should always extract our air from the top and induce it in the bottom, of course, to work with the density. But we cannot rely on the density too much. So jet mixing and diffusivity is more important than density when we're talking about the systems that we would make. So what do we need now when we have covered a little bit about release here? So what do we need for ignition? We, of course, need to be within the flammability limit. So this is, should be a 4 there, of course. This is methane, and this is hydrogen. And the colored part are parts where we are within the flammability limit. And as expected, we have a quite narrow here in the mixing zone, but almost all of the hydrogen is in the flammable region. So we have a lot higher probability of ignition source being actually in the flammable region. We also need an ignition source of sufficient strength. And as we heard before here, it's much higher for propane and methane. But we can also acknowledge that we have to be a bit higher in the concentration before it becomes so low. So close here to the lower flammability limit, we're not, it's still a big difference, but it's not as big different. But the good news is that, or I don't know if it's good or bad news, but most ignition sources are higher. It would be able to ignite also the methane and propane mixtures. There are some ignition sources in this region here, but they're not as abundant. But all in all, ignition is much more likely. It's not guaranteed, so we cannot base our design on that we will have an ignition, because ignition is not necessarily a bad thing. In hydrogen system, it's actually often a good thing, because then we don't have this kind of pre-mixing of air and hydrogen that can go into explosion. And just some other thing that is interesting but not possible to go into here is that we also have spontaneous ignition of hydrogen. It's called diffusion ignition. I will not be able to describe what that is, but we can have, if we have a sudden release at high pressure, it can basically catch up with its own pressure wave. But we will do that some other time, maybe. As Mohammed talked about, flame length is important because it will influence a lot of things: distance to ignition, distance to injuries on people. So this is very important when we talk about consequences, and this is typically deciding on safety distances. So we can see here that we have it's basically a linear dependence on diameter. So if we have 3 times the hole size, we have 3 times the flame length. That is nice. This is based on, to get back to your question here, it's based on circular holes. Most of our leaks are not circular. If we have like a leak in a connection, we would have a not so wide, what do you call it? And that would give us significantly shorter distances because we would induce a lot of more mixing into the flame. A good thing is that when we're looking at the dependence on pressure, we don't see linear dependence. It's exponentially decreasing. So when we talk about these high pressures where we often store, it's not as huge a difference from here where we would more typically store our gases. It will not be twice the length, and especially not 3 times or whatever the pressure increases are. Another thing is the radiation part of it. This is 2 different leak sizes, 1 small leak, 1 millimeter and 200 bar, and 1 large leak, 6 millimeter and 700 bar. And that would, of course, influence the flame length. The black line here is the flame length. And then we have 3 different radiation levels, as seen up there. 20 kilowatts is sort of an assumed ignition radiation for wood. Ignition of wood with the jet flame is complicated, but we will not talk about that either. But and then we have here it would be dangerous to stand for a long time, for a short time, and here for a long time for humans. What is really interesting here is that the distance to dangerous situation is on the order of the flame length. So it's quite similar, and that's not unexpected because we have a very low radiative fraction for hydrogen. And also with the high pressures, we don't see these kind of banana-shaped jets that we would see for a typical hydrocarbon release. As we saw in the beginning, it will be very directional. So we will have a very small thing that radiates on somebody standing here. So radiation is actually not a huge problem when it comes to safety distances anyway. But the problem is that a lot of consultants still use radiation as an injury criteria for humans since they're used to hydrocarbons. A much bigger problem when it comes to hydrogen is the gas temperature, because, of course, the things that are coming out of the flame, as we saw, were very hot. Also, the combustion products will be very hot. They will also be very humid, which is also very dangerous, especially if you inhale it. So we will see dangerous gas temperature levels at double or 3 times the flame length. So this will be more important compared to the radiation, at least when it comes to safety distances. It's actually quite nice that the temperature of the jet flame, if you normalize it or you divide it by the flame length, you will have the same temperature profile. So you can actually, the centerline profile. So you can actually calculate that quite well if you know the flame length. We've also been talking a little bit about flame visibility. This is a little bit Swinglish. I made this presentation just in the break here, so it might be a little bit Swinglish. So we have, here is ultraviolet regime, and here's infrared. So we can see that we have a lot of ultraviolet radiation, and then decreasing here. This is what makes it the blue tint of the flame, and here we have the combustion product, the water vapor, radiating. So we would expect an invisible flame. And we do, from time to time, get invisible flames, as we also saw in the presentation, not with the thermal imaging, but in the open. But we also get, quite often, a luminous flame. This is some experiment I did some time ago. The main reason for this, and we can also see this is some other experiment I did. I will probably mention those later on also. This is without sprinkler and this with sprinkler. And that sort of gives us an idea why would we see this yellowish flame. And the reason is that we would pull droplets into the fuel stream at the nozzle. And then that, because would excite when it goes through the flame sheet, and that would emit this kind of yellowish flame. So this is the main thing. Some of you might have heard of the old Thomson effect. Someone nodding. Because sometimes people say that is this spontaneous ignition mechanism, but they must have been asleep during their thermodynamics, because it does increase in temperature when it expands, but when you accelerate a fluid, it will decrease in temperature to get the kinetic energy. So we will actually have a lot of very cold, this will be very cold. So I actually we had condensation on the nozzle there. Here I actually had problems with ice formation on the nozzle when I did the experiments. So we have ice accumulating, and then it will shoot away like a bullet. It actually deformed the tank. Another hazard we maybe not always think about. Not to only go to theory, I just wanted to show 2 accidents, quite recent. Or this is not extremely recent. This was Sandvika in 2019, as you probably most of you have heard of, where we had a pressure wave throwing sheets of metal. Was it 30 meters maybe? And what was interesting here, and we didn't have any confinement, or not, at least it wasn't fully confined. The reason was that we had this unignited jet impinging on the surface, and that would induce a lot of turbulence here. So when we have ignition, we would have a very distorted flame, and that would increase the flame speed significantly, and in this case, it actually went to detonation. We sort of knew this before. We've seen this in experiments. Health and Safety Executive in the UK have done some experiments about pressure increase from impinging jets before, but it's been on like the 200 bar pressures. So you would see some pressure, but not too much. This was from the 950 bar storage, and in this case, it actually went to detonation. At least that's what sort of the modeling done afterwards tells us. So this was really interesting because we haven't seen this before. 2 accidents you probably didn't hear about was in Sweden, in Mariestad, in March. It was actually 2 independent accidents at the same refueling station in the same month, in different parts of the system. And that sort of tells us, because I mean, we have a lot of experience from industry regarding hydrogen use, especially from the refineries. But they know, their experience when you talk to them is they have leak all the time. They put all their equipment outdoors because it will leak. It has a very low viscosity, etc. So it will go through anything. So it's important to learn from the industry, but it's also that we apply the same kind of systems if we build on that experience. So what happened here was that in the first accident, this is still, I'm involved in the accident investigation here together with MSB. So it's not final, so this is sort of a first impressions, so to say. We had leak on the top here where they have the 950 bar storage. And this was mounted into the pressure vessel. And what they think is due to vibration from the compressor, it sort of started to open a little bit. And you have this kind of bleed hole here. So you always have that, or you should have that, because when you mount it, you would put a fluid here to see if it forms a bubble, to see if that is like really tight when you do it. So here we had a 950 bar jet going out. It didn't ignite. Then we could probably have had a Sandvika. It could have been worse because you have a lot of tanks around here. And it also tells us that it is important to have this hole upwards so you don't have an impinging jet if you have a leak here. So very practical and very useful, I think, lesson so far. Here we have a 9 kilogram of hydrogen, which is a lot. Doesn't sound a lot maybe, but you know the density. Then we have another leak, which was in this container here, we had one of those switch lock coupling, totally dismounting. And here they last 32 kilos in this container. And that's very much. And this is also the full bore rupture scenario that we don't want to account for when we do risk analysis, because that would give us too long distances. So just to show this, you saw the first accident from Sandvika, which could be one of the scenarios. Other one could potentially. It's a large boom. I can put the link in the presentation later on. And this sort of throws these container walls 30 meters away. That was explosion. We have the other scenario we heard about this morning, which is the tank rupture scenario. It can be due to when it comes to transportation. We had experiences with tank ruptures due to mechanical impact on a number of occasions. But so we should of course prevent by different measures to not have mechanical impact. But we can also have this problem if we expose it to temperature, because what would happen when we heat because this is the type of tank that we would use, type 4 tank, where we have a carbon fiber or glass fiber material out here, and then we have a plastic liner on the inside. So when we heat this material up to 130 degrees centigrade, it will start to lose its strength, or it will lose most of its strength. Then, of course, you have it will still insulate the material inside, so it will be a gradual. So if you heat one of those to 130, it will not go like this directly, of course, but it will take quite some time. So you need a temperature-activated pressure relief device. This is mandatory for transport. It's not necessarily mandatory for stationary. It's not stated in most codes, as far as I know. And there might also be some issues with getting the right components here. But the problem is that a lot of people replace that with a pressure relief device, a pressure-activated pressure relief device, like a pressure relief device, yeah. So that activates on high pressure, but that will not work, because if you expose this tank to heat, it will only increase in pressure approximately 10% before it goes into rupture. The reason that people do this is that they have experience from steel tanks, where the problem is the increased internal pressure. That is what would induce your tank rupture. That is not the case for these kind of composite tanks. Oh, I have very little time, I realize. And it's extremely high pressures we're talking about. It's important to acknowledge that in this case, they dismounted the pressure relief device because of an experiment. But I've done a review of accidents, and this happened too often, I think. So this is supposed to be for 700 bar, but they only charge it to 350 bar, I think. And after this incident, they found this chassis 22 meters away from the original place. So it's very high pressures being stored. And going back to the Sandvika, to Mariestad, the problem is that you have to pressure test the entire system up to 1.42 times the working pressure, but nobody dares to do that. I mean, you're supposed to do that on 1,000 bars, so it's 1,400 bars. And it was very interesting. I was at a seminar where both the legislator and one of the major inspecting companies said that they don't dare to do that. So maybe we shouldn't use that pressure. Also, what is interesting when it comes to hydrogen, because you have two sources of energy for tank rupture. One is expansion of the gases. That is one energy. And that's the only energy when it comes to CNG and other gases, because they will first expand and then they will burn as a fireball. In this case, they will burn at the same time scale. So actually, when we add combustion, we would increase the distances to safe by a lot. This is for a vehicle. and this is for stationary. It's not so much here because it's not as turbulent as maybe as that one. And also when we have, for CNG, if we have a rupture, it will only expand, and sometimes it ignites, sometimes it doesn't. I have never seen a tank rupture experiment with hydrogen that does not ignite. It will always ignite. Yeah. An alternative to this pressure release device is a heat leak not burst, where they design it so that the engine liner melts. I will not be able to cover this. But I think it's important to acknowledge that there are such technology. Oh, in the last 5 minutes, I will give my 15-20-minute presentation about our research. But I actually think that the first part here is more important than what we are doing, because there's a lot of literature out there. So this is still a very brief, just the things that I really, really wanted to say about hydrogen safety. But we basically have 3 different areas: risk-based and regulation, codes and standards kind of work. We have experiments, and we have simulation and model development. I would say that we do most here, probably, and probably most jet fires related. But we also do a lot risk-based and codes. And that takes, I think, all of my time, almost. I should be doing the other projects as well. But there are a lot of things going in the Swedish legislation right now. And I work very close to Swedish MSB. Some experiments, when we have, this, of course, this very flammable gas, we need to detect it really, really quick. The most common method is these kind of typical catalytic detectors. But then you have to have agglomeration somewhere before you can detect it. And outdoor, it's almost impossible. So it's much nicer to use sound. And there are some commercial sound detectors out there. But they're very, I mean, I've been testing them a bit. I had a master thesis, I think last year, year before that tested a commercial. And they were quite bad from my perspective. I mean, we could hear it much, much easier with our ears than this one could hear. Because that's one thing that is important. You will not miss a leak. You will not see it, but you will definitely hear it. We did experiments on 0.09 millimeter leak sizes, which is very, very tiny from a coupling. And we could easily hear that from way, way away. These are some other experiments. So we used good but normal detectors, because that's the other thing, that the commercial detectors are quite pricey, like 13,000 euro for one detector. This is 7,000 euro? No, 7 euro. Wait. What was it? Yeah, 700 euro. Yeah, and this is the signal that we detect from this was from the smallest leak of all. Here we got, this is frequency on the y-axis and time on the x-axis. Here is the wind. It was a quite windy day. And here we can see really clearly the leak. So I worked together with some artificial intelligence researchers, putting this into a network. Some experiments about an impinging jet on a tank, where we just wanted to see, because there have been some designs where they tried to prevent tank ruptures with a sprinkler system, and so MSB wanted that tested, and it didn't work, at least not for composites. It could work for steel. We've done some experiments with shooting, because together with RISE in Sweden, because the Swedish rescue services are using shooting to depressurize vessels. They've been doing it on a number of occasions where it's difficult, it's dangerous to tow the vehicle away without first getting it away. And it can, yes, they had a jet fire also that sort of threw the car away afterwards. Some ongoing experimental projects. We're testing barrier materials for hydrogen jets. I don't know if anybody from Everfuel is here. I'm doing some tests together with Everfuel to see what kind of barrier materials that works for hydrogen. I'm looking at buoyancy effects for combustion products, because now we don't know when it goes up. As we saw, we have very long distances to high temperature. So temperature is what is determining our safety distances. But we need to be able to account for that to reduce the distances. We're testing some aerosols for inerting materials. We do have some experimental from micro to meso to macro scale. This is some experiment by University of Southeastern Norway that we will make out in Revinge, where we have our container. This is an explosion in the upper one. You probably don't see it because it's totally open, so we just release it there. And then here we have with obstructions in the form of pellets. So even though this is didn't it start? I have some issues with my. Oh, everything will out. It will be too loud. So you actually take it one more time. So even though it was totally open, it was very clear. And in this case, it's barely visible. You can see some wobbling of the steel. And this is 300 grams of hydrogen, and probably most of it leaked out through the doors before we ignited it, or they ignited it. We will do this out in Revinge, and maybe together with DBI, we have some discussions. Simulation, did some for standback distances for rescue services. I did a lot of CFD simulations for different scenarios to try to figure out, because they have just developed some guidelines for the rescue services when responding to this kind of vehicle accidents. So I did some simulations to inform that work. I already said that we don't have a layer for the advanced CFD models. The problem is that they take a lot of time, so we're building another model, what is called a multi-zone model for this kind of ventilation project. It will also be used for the new legislation, because the Swedish Civil Continuous Agency, who is responsible for flammable goods legislation, they are revising it, and I'm working. I mean, the week before, 2 weeks ago, I sat down with them for a full week almost, trying to actually typing in the legislation. And what takes most of my time now is the first bullet here, and that is safety distances for the revised Swedish legislation. So actually, the Swedish Civil Continuous, just give us a table, so to say, so we can know how we can install this, because that is a big mess in Sweden right now. I'm working together in a working group with Swedish Gas Association with specific guides for refueling stations. I have involved in a project together with the Swedish military, because they're also thinking about hydrogen for their military platforms, which puts other scenarios on the table. But it's quite interesting. I'm in a working group with the International Energy Agency, sort of trying to put all these things together. Runefors, I already talked about this HySave. Work a little bit with Volvo. Volvo want to put their first hydrogen truck on the market in 2025. So it's quite soon, and of course they want some discussions, some projects. And what's actually, I said that the last one took most of my time, probably this one, the presentations in various situations, because it seems like all conferences want a piece of hydrogen nowadays. This was extremely chunked, because this wasn't really my plan for this presentation. You will get the presentation afterwards, but you're also very welcome to contact me if you have any questions or something.